This is Physical Chemistry, Part 3, Quantum Chemistry, Chapter 21, Many Electron Atoms, Section 21.1, Helium, the smallest many electron atom. In quantum mechanics, when we say many electron, that means two or more electrons. A helium atom consists of a nucleus and two electrons. So we have two protons in the nucleus, and then two electrons outside the nucleus. We can use two vectors, R1 and R2, to specify the positions of the two electrons. Pay attention here. This is a little misleading. The magnitude of R1 can be different from the magnitude of R2, and they do not have to point to the opposite directions. So you can have one electron here and a second electron maybe here. That's possible. So these two electrons may appear in any position in the entire space. The Schrodinger equation for the two electrons in the helium atom in the Cartesian coordinates can be expressed as this. First, we have the kinetic energy of electron 1, kinetic energy of electron 2. This is attraction between the electron and the two protons in the nucleus. This is attraction between electron 2. So that's why I put R2 here. This is attraction between electron 2 and the two protons in the nucleus. This is the repulsion between the two electrons. So psi is of R1 and R2. R1 and R2 are two vectors. It's just more convenient for me to use bold font instead of putting arrows on top of R1 and R2. So this R1 is this R1 vector, this R2 is this R2 vector. And now this Laplacian operator is the sum of these three second derivatives in terms of x, y, and z. Now this R1 is the square root of x1 squared plus xy1 squared plus z1 squared. This R2 is the square root of x2 squared plus y2 squared plus z2 squared. What about this R12? This R12 is the magnitude of the difference between these two vectors. So R12 actually has a much more complex expression. R12 is the square root of the sum of three terms. The first term is x1 minus x2 squared. The second term is y1 minus y2 squared. The third term is z1 minus z2 squared. So now let's write out the Schrodinger equation in the atomic units. Over here, you see four fundamental atomic units. The charge of an electron is one atomic unit of charge. The mass of an electron is one atomic unit of mass. H bar is one atomic unit of angular momentum, and 1 over 4 pi epsilon 0 is one atomic unit of Coulomb's constant. Now we can rewrite the Schrodinger equation in the atomic units. Well, this is much simpler. The kinetic energy of electron 1, the kinetic energy of electron 2, the attraction electron 1 feels, the attraction electron 2 feels. And pay attention to this number 2. These are the number of protons in the nucleus. And over here, plus 1 over R12, this is the repulsion between the two electrons. Now, what about this delta? I'm going to express this delta in spherical polar coordinates for electrons 1 and 2. So this is for electron 1. And this is the Laplacian for electron 1. This is Laplacian for electron 2. How do we solve this Schrodinger equation? I mean, it looks simpler, but if you look at this R12, you have the coordinates of electron 1 and the coordinates of electron 2 correlated, strongly correlated to each other. There's no way to separate the coordinates of electron 1 from the coordinates of electron 2. So it's extremely difficult to solve this Schrodinger equation for this two-electron system. But by making some approximations, we can solve the Schrodinger equation approximately. So first, let's just assume that we can, separate the wave function of electron 1 from the wave function of electron 2. That means we can write this wave function of the two electrons as a product of two functions. The first function is the wave function of electron 1. The second function is a function of electron 2. So by doing this, we are assuming the motions and the positions of these two electrons are independent of each other. This phi 1 and phi 2 are the one electron wave functions for these two electrons. So they are also called orbitals. And I'm not going to show you the derivation, so I'm going to just show you one approximate solution to this Schrodinger equation, which is this. Let's say phi 1 is e to the power of negative zeta r1. Phi 2 is e to the power of negative zeta I2. And then the total wave function of the two electrons is simply e to the power of negative zeta r1 times e to the power of negative zeta r2. Zeta is the effective nuclear charge felt by the electron. So I'm just pretending right here we are dealing with one electron system for each of the two electrons. For electron 1, let's assume this electron 1 feels attraction from the two protons. And then 0.31 charge of repulsion from electron 2. So that's the electron shielding. So you have attraction from two protons and repulsion from 0.31 electron. You take the difference. Well, the effective nuclear charge is 1.69. So I want you to imagine this case. You have a one electron system. Okay, there's only one electron and one nucleus. And inside the nucleus, you have 1.69 protons. It's not one proton, it's not two protons, it's 1.69 protons. And then you solve the Schrodinger equation for that one electron system, and you will get this wave function, e to the power of negative 1.69 times r for that electron. Again, this zeta is the effective nuclear charge, and here's a table of effective nuclear charges for selected atoms. If you look at helium, it's 1.69. You can get this value by experimental measurement or by quantum mechanical calculations.